Hello, this is the second of the fourth Matrices series for OCR AS Core Pure Further Mathematics, and will cover finding the determinant of a 3x3 matrix. We have already looked at the determinant of a 2x2 matrix in previous videos. We use the notation det T equals what looks like the modulus of T, or the modulus of the matrix ABCD, and we know that this equals AD minus BC. Let us consider a 2x2 matrix using different notation, similar to that used for the 3x3 matrix in the previous video. So here a 2x2 matrix is denoted by A1, A2 and B1, B2. Then that determinant of A, denoted by what looks like modulus of A, is of course just a number that can be evaluated as A1, B2 minus A2, B1. This is just the same as AD minus BC. The determinant of a 3x3 matrix can be found from the cofactors of any row or column of the matrix. You will remember we worked out how to find minors and cofactors in the previous video. Each element in that row or column is multiplied by its cofactor, and the results are added together. For example, the determinant of a 3x3 matrix A can be found from the first column, using det A equals A1 capital A1 plus A2 capital A2 plus A3 capital A3. You will remember that the capitals are what denotes the cofactors, and that the small letters are the elements of the original matrix. Finding the determinant by using the first column is called expansion by the first column. So, using the notation for a 3x3 matrix of first column being all the small a's, second column being the small b's, and third column the small c's, with a cofactor matrix using capital letters, then we would find a similar formula applies to any row or column of the matrix. In other words, the determinant can be given by expansion of any row or column. An example here, expansion by the first row, in which case we would write det A equals A1 A1 plus B1 B1 plus C1 C1. In this example here, we will find the determinant by expanding by the first column of this matrix. The formula would be det A equals A1 A1 plus A2 A2 plus A3 A3. So you can see that, as we did before in previous videos, we've got that first element A1, which is a 5. We've crossed out the row and column which are associated with that first element A1, and then we would have a think about the signs in the sign matrix off to the right. So we would have a plus, because that's the sign over here. We know we've got that element of 5. And then we know we're going to be working out that cofactor from this 2x2 matrix over there. We would then move along, and we know that we're looking for A2, which in this case is minus 3. We know we're going to have a minus sign in this case. So far we've done that part. Now we are adding, and we've got the negative sign, and we've got a negative 3. And if we were to circle and cross out that row and column, you can see that the matrix would be 1 minus 2 minus 1, 4. In other words, we've put the components of A2 together. Moving along then, we're now going to add A3. We can see that it's, in this case, a positive, but I'll still put it in the brackets is a positive, so you can see what I'm doing. And we have an 8 as the A3 element. If I was to cross out, obviously that first column still cross out that third row, then the matrix, the 2 by 2 matrix I'd be left with would be 1, minus 2, 2, 3. When we work this out, we get 5 times, and then that determinant is then 8 minus 3. If we look at the signs here, we're going to end up with a positive 3 times the determinant, which is 4 minus what ends up being plus 2. And then we're going to have plus 8, 3 minus a minus 4. This will give us 55 plus 6 plus 56, which totals to 117. This then, expanding by the first column, is the determinant value for this particular 3 by 3 matrix example. Here you can see it written out rather more neatly. You may wish to pause the video here and check this through carefully for yourselves. We could have found a determinant by expanding any other row or column. So for example, let's double check our result by expanding by the third row. If we expand by the third row, in other words the 8, the minus 1 and the 4, then the formula we would use would be det A equals A3 plus B3 plus C3 C3. So let's start off with the 8. As you can see, the first column and third row are eliminated, and we would have a positive sign. So we've got positive of our element 8, and the 2 by 2 matrix is 1, minus 2, 2, 3. Moving along then, we would have a negative as our sign from the signs matrix. We also have our negative 1 as the B3 element, and our 2 by 2 matrix would be 5 minus 2 minus 3, 3. Adding that third C3, C3, we know we're going to have a positive sign. Looking at the signs matrix, we know the element is a 4, and the matrix, 2 by 2 matrix, is going to be 5, 1, minus 3, 2. When we work all that out carefully, taking note of the signs, we would find that we had 8 times 7 plus 9 plus 4 times 13, which would again total to 117. As expected, exactly the same value for the determinant of that matrix. So to reiterate, whichever row or column you use, the expansion of a determinant will simplify to the following expression. The determinant is the same no matter which row or column is used in the calculation. However, you can save work by choosing the row or column carefully. For example, if one of the elements in the column or row was 0, there would be no need to calculate the cofactor for that element. So, if possible, you should choose a row or column which contains one or more zeros to save yourself some time. In this example here, where n is given, we can see that we might choose to expand the determinant by the second row because there is a 0 in the second row. Of course, we could also have chosen the first column. For the trivial example of a 1 by 1 matrix, the determinant would be the single entry. We can see a similarity between determinants of other n by n or square matrices. For a 2 by 2 matrix, we know that the determinant was A1b2 minus A2b1. And for a 3 by 3 matrix, we have this slightly more convoluted expression, which we have investigated as to where that came from. For a 4 by 4 matrix, you would need to find 4 cofactors, each of which involves finding the determinant of a 3 by 3 matrix, so it's quite long-winded to do this by hand. And you can see the advantage of a calculator or other computer method. Here is an example that would aim to test your understanding as well as your calculator use. It may be quickest to choose to expand by the third row or column due to the 0 element. And do check your answer at the end by using your calculator. I'm choosing to use the third column, so I can write down my formula for the determinant of A as being C1, C1 plus C2, C2 plus C3, C3. I probably will remember my matrix of signs, but starting then with this element here, C1, I'm going to have a positive X, and then I'm going to have the remaining matrix 2x, x2 to work out the determinant of. I'm going to have then my negative sign and 3, and my remaining matrix of 1, 1, x and 2. And then I'm going to have my plus 0, which was one of the reasons that I chose that column, because it saved me some work. If I expand that out, I know I'm going to have x, and it's going to be 4 minus x squared as the determinant. And then I'm going to have a minus 3, 2 minus x. That is the equation for the determinant, and I'm told up here that it equals 0. If I tidy up the algebra a little bit, I should get that x cubed minus 7x plus 6 equals 0. Let's try x equals 2. Well, if I had 2 cubed minus 7 times 2 plus 6, that would be 8 minus 14 plus 6 does indeed equal 0. So I have verified or shown that x equals 2 is one root of that equation. I could then work out the other two roots by various methods, but I'm going to try and do it by inspection, because for me that's the easiest way of doing it. So I know that x minus 2 is one of the factors of x cubed minus 7x plus 6 equals 0. I know I'm going to just need an x squared term in order to get the x cubed. I have an unknown number of x's in that quadratic factor, but I know that whatever the constant factor is, that minus 2 times that must give me plus 6. Therefore, I immediately know that I have to have a minus 3 there. I can see that I have no x squareds in that x cubed minus 7x plus 6, but that must be the same as minus 2x squared and plus kx squared. Which would give me that k must equal 2. Then all I have to do is to factorise, and excuse me for working up here, x squared plus 2x minus 3 me to x plus 3 x minus 1 and the other two roots are therefore x equals 1 or -3. In the next session, we will find the inverse of a 3 by 3 matrix.